Okay, so our webinar today, presenting results on analysis of greenhouse gas emissions from different residential heating technologies, where the analysis was conducted across the US. Just want to acknowledge our affiliate Train Technologies for funding this research, and the research was conducted by Nelson Diechter and Aref Abou. The objective of the study was to analyze annual changes to greenhouse gas emissions that result from replacing a residential gas furnace with a heat pump, where the heat pump had various options for both speed capability and backup heat on the existing electric grid. So for example, down here you can see the baseline is a natural gas furnace, and heat pump options are a single speed or variable speed heat pump. And then each of those heat pumps can operate with either electric resistance backup heat or gas furnace backup. In both cases, when the heat pump is not able to meet the load, either the electric resistance or the gas backup kicks in, and it does not run simultaneously with the heat pump. We analyzed the results across various geographic regions in the USA. You can see those regions here. So across those regions, we analyzed over 200 locations in the US, and we selected those locations based on a unique combination of the electric grid and the DOE climate zone. So up here on the top right is a map from WattTime that outlines the electric grid operator regions in the US. And so you can see some of the borders here. Some of them are along state lines and some of them cross state lines. And then on the bottom picture here, you can see the DOE climate zones. And so basically what we did was we looked at the overlapping intersection between the grid and the climate zone, and then we selected the most populated city in each location. And then we look at the results at a higher level. We aggregate the results for entire states and regions based on populated weighted averages of those cities. Taking a step back here and just looking at overall electricity production, this is electricity production in 2018 as reported by the US Energy Information Administration. You can see that the dominant source of fuel on the electric grid is is natural gas, followed by coal, nuclear, and renewables, where renewables include solar, wind, and hydroelectric power. Just to give you an idea of emissions associated with natural gas and coal, on average, natural gas is approximately 0.9 pounds of CO2 per kilowatt hour, and coal is 2 pounds per kilowatt hour. So it's a significant difference for those two fossil fuels. When we look at US electricity production by state, you can see there's a very wide variation among states. So here we have the percent of the electricity contribution on the y-axis and the states on the x-axis. So you can see some states have large percentage of renewables, others insignificant, as well as quite a bit of variation in natural gas and coal. In addition to thinking about the average fuel consumption and emissions over the course of a year, what's really important in conducting an analysis of emissions associated with heat pumps is considering the hourly CO2 emissions. So just to give you an idea of how the hour of the year is important, here's an example day from California on August 10th, 2018. And on the Y1 axis, we have supply, and the Y2 axis, we have average emissions intensity in terms of CO2 per kilowatt hour. You can see here we've got natural gas and some nuclear as a base load. We've got some imports, and then we've got, this is the solar PV in the middle of the day. And so you can see that that solar PV reduces the average emissions intensity in the state of California on this day. What I just showed you in the previous plot was the average emissions. However, in this study, we use the marginal emissions rates associated with electricity production. So marginal emissions rates are the emission intensity of the marginal generators used to meet incremental loads on the grid. Our study used historical 2019 marginal emissions rates that were reported every 5 minutes and calculated by watt time. Watt time's methodology in calculating marginal emissions rates is quite detailed, and I don't have time to go into it here, so I went ahead and put a link for you so you can learn more about their methodology. The Watt Time publishes on their website the current marginal emissions across the US by location. They do store historical data, and we obtained it from them under an NDA. Our reasoning for using marginal emissions rates is thinking about the replacement of a furnace with a heat pump reflects a new electric load in that it would operate essentially on the margin. So if we're adding in the winter, if we're adding this heating load that's electric that wasn't previously there, then this could be considered to operate on the margins of the electric grid. It's important to realize that future investments in electricity generation will impact emissions rates associated with heat pumps, and we do not model that here. So for example, if in support of electrification of heat pumps, utilities develop new assets specifically to meet those loads, and those are renewable, then that will change these answers. So we're specifically showing here what happens today on the current grid. I guess I should say in 2019, on the 2019 grid. So thinking about how marginal emissions rates vary over location and over time, here is just a plot of the marginal emissions rates in California. So you can see here hour of the day versus the marginal emission rate on the y-axis. You can see that the marginal emission rate varies over the course of the day and also by season. So it's lowest in the spring based on solar generation, and higher in the winter, and higher in the evenings and at night. The marginal emission rate is always higher than the average carbon intensity on the grid. In Montana, the marginal emissions rate is very consistent and also quite high. This is a result of coal being, the marginal emission rate being attributed to coal. So basically in Montana, coal generation is used to meet those marginal emissions. Those were just two examples. If this plot shows for every state, the average marginal emissions rate, as well as the minimum and the maximum for that state, you can see some states have a lot of variation. For example, Florida, Arizona, Washington, Vermont, and then other states have very little variation. So, for example, over here, Louisiana, Arkansas, Ohio. So the analysis really changes depending on geographic location. So what we did to conduct this hourly analysis is that we built an Energy Plus simulation of a residential home. The home has 2,400 square feet of conditioned space and 1,200 square feet of unconditioned attic space. It's a wood frame structure with R13 wall insulation and R19 attic insulation. And in order to determine the home construction, we did a sensitivity analysis to look at how the results changed by construction type. And we determined that construction impacts the magnitude of emissions for all cases, but it has little effect on the percent change in emissions and the relative ranking of results. Although this is a typical type of home construction, it's not necessarily representative of the average home construction in the US. However, we don't expect that to change the overall conclusions of the study. I also will mention here that in order to run the simulation, we had the 2019 watt time data as I described. We also pulled the coincident 2019 weather for those cities as well. So we ran this model with the 2019 emissions data and the 2019 weather data. That gives us the result for 2019. Now, that's not a typical meteorological year, so that if unusual weather patterns in any geographic location would affect the result for that particular year. So then just to talk a little bit about the systems we modeled. So there are 4 types of HVAC systems as I described earlier. The baseline was a single speed air conditioner with gas furnace. And then in comparison, we modeled a single speed electric heat pump with electric resistance backup, then switched that to variable speed, also with electric resistance backup. Then we used a single speed heat pump with gas backup. This product is in the market, also called a dual fuel system. And then we also switched that to variable speed as well. And as far as heat pump capacity sizing, we auto-sized the heat pump capacity so that the rated capacity at the rating conditions for the heat pump was 1.4 times the design day load. Sizing factors ranged from, typical sizing factors in construction are within this range, approximately 1.33 to 1.48. And so that's how we picked the 1.4 factor. And as I mentioned, the backup heat operates when the indoor temperature drops below the indoor set point, which was 68 degrees, and the heat pump shuts off when the backup heat operates. Okay, so here are our results. This shows, I have these grouped by region, and I have quite a few plots here covering the whole US. So let me just give a little overview of how to interpret these. So on the y-axis, we have a CO2 reduction. So a green number is good, essentially, and a red number is bad, meaning there's an increase in emissions. And so you can see here in California, this is in comparison to a gas furnace. Changing to a heat pump with electric backup would have a approximately 15% reduction in CO2 emissions. Increasing to variable speed would increase savings up to about 40%. However, if we look at the gas backup in comparison, the savings are actually greater than the electric backup based on that 2019 data. This tends to hold true across this holds true across all of the states that I'm going to show you, that the variable speed generally has greater savings than the single speed, and the gas backup generally has a better result than the electric backup. Again, on the 2019 grid. Here's the results for Oregon and Washington. You can see this actually results in a CO2 emission increase over a gas furnace. If we switch to the Southeast region, you can see here almost all systems in all states showing an increase in CO2 emissions. There are a few cases where the variable speed heat pump with the gas backup does generate some savings. Here's the Midwest region. Again, not looking real great. All states resulting in a CO2 emissions increase. When we go to the Northeast, the situation improves. So we have several states here showing an improvement, Connecticut, Rhode Island, Vermont, New York. And generally, if we look at this from a high level, the results here tend to correlate to the amount of coal being used to meet those marginal emissions, the marginal emission rate. Here's the Rocky Mountain region. Just give everybody a minute to digest this. Some savings in Idaho and Nevada. And the Southwest. If we go take go look at this on a high level, we see that if we look at basically the number of states where we get a benefit from the heat pump in terms of CO2 emission reduction, we see a benefit in 15 states for the variable speed heat pump with gas backup. We see 9 states benefit from the single speed heat pump with gas backup, 8 for the variable speed heat pump with electric resistance backup, and 4, oh, sorry, I've got a typo here. This is the single speed heat pump with electric backup down here with 4 states. So I think this is really important to realize what results we might see today on today's grid, but there's also the grid is also changing quickly as coal plants are retired and more renewables are brought onto the grid. And so this plot here, the purpose of this is to show if we fast forward into the future and we envision 100% decarbonized grid, but let's say today, single speed or variable speed electric heat pumps are installed with this natural gas backup. The question is, what will that look like on 100% decarbonized grid? Essentially, how much gas are we going to be using, and what will that penalty be 20 years from now? So what this shows is the percent CO2 reduction compared to today for 100% decarbonized grid. So an all electric heat pump would just be 100% reduction. So you can see here, even with the gas backup, the variable speed is still achieving an emissions reduction in excess of 80%, and the single speed system is achieving an emissions reduction between 65 and 85%. So this is an interesting way to think about how we transition to a 100% decarbonized grid in the future, potentially using electric heat pumps with gas backup today could be a more beneficial transition strategy that can get us to a decarbonized grid in certain locations where marginal emission rates are high, which is a lot of the US currently. So I want to talk about some of the limitations of this study. So as I've mentioned, we did not consider future investments in renewables on the electricity grid that will certainly improve the CO2 emissions associated with electric heat pumps. This, again, using 2019 data, shows us essentially where we were in 2019. We expect the situation will improve from there. And similarly, not including coal retirement from the electricity grid. We plan to address, we're working on like a second phase of the study funded by NRDC that we are looking at the potential future grid scenarios. We also did not consider the impacts of global warming potential resulting from leaks in the natural gas system, methane leaks, or refrigerant leaks. So neither of those are included in the analysis. You may have seen a webinar from WCEC before on the difference between equipment efficiency and system efficiencies for HVAC systems, particularly variable speed systems, including the effect of duct system losses. We have not included that here. What we've modeled here are manufacturer equipment efficiency curves for these heat pump models that I've shown you. If we include system efficiencies, you would expect the difference between single speed and variable speed to potentially, you might expect some losses in the variable speed systems unless zoning is included. So that's a whole nother topic I'm not going to get too much in today, but we do have another webinar on our website about that. We also do not consider the local environmental impacts of full electrification. So we're just looking here at overall CO2 emissions. We're not looking at local pollutants associated with burning natural gas. And we're also not considering here the cost of the technology or of the natural gas infrastructure installation and maintenance. So for example, if we talk about retaining natural gas furnaces today, that might be a different decision that's made in a retrofit application versus building a whole new community, right? Like, does it make sense to run natural gas infrastructure today in residential communities, for example? So we don't consider those trade-offs here. But with all those disclaimers, our conclusions are that in regions of the US where marginal CO2 emissions rates are high, electrification with heat pumps may actually increase overall CO2 emissions, and that heat pumps with backup gas heat may have lower emissions compared to all electric heat pumps. If we install those heat pumps with backup gas heat today on a future all renewable grid, variable speed heat pumps with natural gas backup could still obtain 83 to 90% of the emission reductions compared to today's natural gas furnace. And that is it. So we will take your questions.
Great. I see one. I'll turn my webcam on. Hello again. I will. We have a couple questions in the queue. So if you are able to unmute yourself, we'll ask you to ask your question directly to Theresa. Jason Leroy, are you available to ask your question?
Now, can you hear me now?
Yes, you're good.
Okay, good. Yeah, my thing just turned green. Did I misunderstand you at the beginning? Did I hear you say that when the backup heat comes on, the electric heat pump turns off?
Yes, that's correct. The gas furnace and the electric heat pump can't run simultaneously.
Okay, but just with the gas furnace, not with electric heat, right?
I believe we simulated the heat pump in the same way. So when I can double check that and get back to you.
Well, okay. So here's what I'll say is that's not at all how the systems operate in the field, right? The heat pump will run, and when it needs additional help, the electric heat will kick in to kind of give it whatever the shortfall in the capacity of the heat pump is. But if you assume that the heat pump turns off completely, now you're going to have a COP of 1, which is going to be, terrible system performance, and that's going to really penalize you. So you really want to run the heat pump as much as possible because it has a high COP.
Okay, great. Thanks for that feedback. I'm actually not certain on that detail as Nelson ran the analysis. So I'll check on that and we'll
Great.
Maybe we can do a short Q&A that goes out with this, Allie.
Yeah. All right, Kevin Duell. Let's see. I'll unmute you here and see if you're available.
Hi. Can you hear me
Hi,
now?
Kevin.
Hi.
Yes.
Had a couple questions. In the decarbonized grid scenario, is that based on fossil gas or any renewable natural gas in the pipeline?
So that's a pretty simple analysis. All we're saying there is if the grid was 100% renewable, meaning that it had no net carbon emissions, however you get there, right? That there's just no carbon emissions associated with electricity reduction. And we're still burning some natural gas because we still have those backup gas furnaces installed. What essentially would be losing because of that? Because
Okay,
we
so
have backup gas heat running, and that just assumes we're burning natural gas, not, it doesn't give any credit for renewable natural gas or anything like that.
gotcha. That's what I figured. And the other question was, what was the efficiency of the baseline gas furnace?
80%.
Okay, cool, thanks.
Okay. There also is a report that we're going to add to the website that has more technical detail in it as well. So
Nice.
we'll share that when we send out the slides.
Thanks.
Great. Any other questions? Please feel free to chat your name or raise your hand, and we will let you ask those. Oh, let's see, Paul Rafferty. Let's see, Paul, I'm going to unmute you.
Hello, can you hear me?
Yeah, yep, sound good, Paul.
First of all, thanks. This is a really interesting study, one I've been curious about, but haven't had time to look at myself. I had one question was, at the moment, the natural gas backup basically operates essentially as a backup, but there's no active fuel switching going on. Did you do any simulations where you kind of dynamically track the marginal emissions rate and then decide whether or not to use natural gas during the day rather than as a backup, right? When is it lower marginal emissions based on the watt time data? Let's use electricity. If it's really high because everyone else is using electricity or there's some weird grid condition, then we use backup natural gas. I think it would be interesting to see what the optimum there would look like and how different that would be from just a kind of default backup.
Yeah, that's interesting. We certainly didn't do that. I mean, that sounds like fun. I guess there were only some states where that, I mean, some
Makes
states
sense,
that would be really interesting, right? Some where the marginal emissions rates don't vary at all, really.
Right.
Will matter, but yeah, in some of these states that would be quite interesting. Like in California, it's interesting. The average and the minimum are quite close together, but then we get just some times where it's really quite high.
Right.
Probably as a result of imports, right? So it would be interesting to base controls on that, and that's, you know, that's where everything is going, right? Basing control decisions on pricing signals and emissions rates and, you know, load shifting and all of that, but have not considered essentially load shifting to gas based on emissions. So it's an interesting idea.
Sure. And then I had one other question about I wasn't sure, is the watt time data, is that emissions per megawatt hour of generation, or is that emissions per megawatt hour of actual delivered to the consumer at their utility meter? Like, does it account for transmission losses?
I believe it is a kilowatt hour delivered to the consumer.
Oh, okay.
At the electric meter, yes.
Okay, cool. Great, thanks again.
Yeah, they have quite a few papers and references on their website. The one I linked to from the presentation, I felt that was the sort of the best description.
Great.
Okay, next question is from Yuho. I'm going to unmute you there.
Hi, can you hear me?
Yes.
Okay. Hi, thank you for the presentation. I just had a question on the Montana number. It's very interesting. I wanted to hear a little bit more on that one. It seems, although they have 50% renewable, but in the same time, they don't seem to vary either seasonally or daily. Do we know why that was the case?
My presumption here is that they're modulating coal plants essentially to meet those marginal demands on the electric grid, so that essentially the renewables form a base load, and then it's the coal plants that are essentially modulated to meet the load. That's it. It's an interesting finding, right? And I've done some reading on, essentially how that works, because going into the study, I assumed that coal plants were base load.
Yeah, exactly. That's why I was
exactly. I know. Yeah. So there's a bunch of, on the Watt Time website, there's a whole bunch of discussion about this, but there is, if you believe the Watt Time methodology, right, then this is essentially the conclusion that they reach, that there is coal being used on the margins in certain states.
Yeah. Okay. It's just very interesting when I saw that. I just kind of want to hear your takes on that. But yeah, I think.
Yeah.
I can see
It surprised us too. I found it surprising.
Yeah. Okay. Thank you.
Great. Thank you. All right, Aaron Weiner, go ahead and unmute you.
Great. Hi, thank you guys so much. I had two questions. The first one is, are your models set up that you could kind of drop in almost like a third option, which would be replacing the existing gas furnace at that performance level with one with like a much higher level of performance, like 130 or 120% AFUE, like a gas heat pump driven furnace?
Yeah, I mean, the whole methodology and all of essentially what we ran here were hundreds of parametric simulations based on this Energy Plus model. And so it is possible for us to drop in a different piece of equipment and run another analysis.
Okay.
That's within the realm of possibility. We are a grant-funded research institution, so
yep.
We do look for people to pay for those types of things.
Yeah. Okay, so we can just follow up with you to find out what would be entailed in doing that.
Yeah.
Awesome. And then my second question was, if you could actually go to the previous slide, the one with California, Oregon, and Washington.
California, Oregon.
Oh yeah, sorry, just California.
Future this one?
No, you were on it. The MERS on California. Sorry, I think I misspoke.
Yeah.
So it seems like things are pretty nice and tight, but then they do go kind of like haywire in just those 2 months, right? May and April, in the later hours. Like, what do you think that's all about?
I believe that's solar in the spring when there's not a bunch of cooling. The cooling load is minimal, but we have a lot of electric PV generation, and so there's sort of this large supply of renewables at this time.
Got it. Cool. Thank you.
Great. And I just put in the chat Theresa's email address, so feel free to follow up with her if you have more specific questions. All right, let's see, Mark Woodruff, I'm going to unmute you.
All right, can you hear me?
Yes.
All right. Well, the guy two questions ago may have partially answered my question, but I'll go ahead and ask it anyway. But so when you were going region by region, you were showing that in some areas of the country, going from a furnace to either a heat pump or a dual fuel system shows a savings, and then in other areas of the country it doesn't, right? And yeah. I think you say it depends on the percentage of their grid that is renewable. And so my question was, is there some really convenient and easy to remember rule of thumb that we can talk about to utilities that says, hey guys, whenever you get to a certain percentage of your grid that's renewable, that's when this starts to make sense, or that's the tipping point, right?
Yeah. I've been trying to produce some plots like that to look for sort of simple rules of thumb. Things definitely get better when you have like less than 15% coal on your grid. It's really getting rid of the coal, because natural gas is kind of a break even. I mean, it depends on your climate, right? Like, what's really great about this is we run an hour by hour simulation looking and then sum up the whole thing. And so, so natural gas is kind of break even, does better in warmer climates than in colder climates because your heat pump efficiency goes up. But it's really getting the coal off the grid that becomes the game changer here.
Got it. Okay, thanks.
Great. I see a question from Thomas Lienhard. I'm going to unmute you, Thomas.
Oh, sorry, I had to unmute myself.
That's
I
okay.
apologize. I have two questions. One has to do with being an engineer. I always want to find the best first thing to do. And when we are talking about devices that are 80 to 97% efficient, being on the marginal grid versus automobiles, which are also coming off of fossil fuels and into the grid right now, has there been any thought of talking about which ones should be done first to keep our carbon emissions at its lowest? In other words, every time we bring a car from fossil fuel onto the grid, it causes higher marginal cost. So has that been rolled in at any time to show which is the best thing to do first to reduce carbon?
Right. So if we're going to decide to electrify a heating load versus to electrify an automobile, which one wins essentially in terms of emissions? I don't know the answer to that. I don't know if that's been done. That's definitely a really interdisciplinary area of research, right? But we do have at UC Davis, we do have an Institute of Transportation Studies. So that's an interesting question. I'm sorry, I don't know the answer.
Okay, my second question is about the operation of heat pumps in ASHRAE climate zones 6 and 7. That's where our service territory is. And we find that the manufacturer's COPs are about double what they actually operate at in real life. And so it's interesting, do you have maybe a knob on your calculations we can turn it down to what we're really seeing in heat pumps so that we can make this calculation actually accurate, because heat pumps don't operate at 45 degrees Fahrenheit constant?
Yeah, so our simulation actually includes performance curves as a function of temperature. So the performance drops off significantly as it gets colder. And all of those performance curves are in the report. If you want to take a look at those, if you think they're way off, I'd be interested to hear about that.
All right, thank you so much.
Okay.
All right, and then I'm going through the list again. It looks like we may have an additional question from Aaron. Aaron, do you have another question? I'm happy to unmute you. Oh, there you go.
I'm sorry, I just realized I neglected to lower my hand. I did not have another question. Thank you.
Oh, no worries. Okay. Well, we still have some time left, so feel free to raise your hand or put your question in the question box, and we're happy to answer your question. I'm going to get you guys a link to the report here and put it in the chat while we're waiting for more questions. There we go. So I'm going to get you a link to the PDF. There we go. So that's available there. All right, Carlos. Carlos, looks like you have a question. I'm going to unmute you.
Yes, can you hear me?
Yes.
Perfect. Yeah, so could you clarify that question? So I see that you took into account the manufacturer performance curves, right, for heat pumps. But if they are really only in effect once there's a turnover from 1 degree below the set point, right? So at 67 degrees or below, that's when they fully, are operational, right? Isn't inadvertently benefiting the heat pump, right, on the models to operate at a higher efficiency that will really happen in real, scenarios, right? Because otherwise, at least in our service territory, most of those heat pumps, are typically only kick on to fully turn over and operate like at 45 degrees or below.
So the way that the model is operating is that the the heat pump itself is trying to meet the indoor set point, which is 68. If there's not, and that heat pump performance curve is a function of outdoor temperature. If the heat pump cannot keep the house at 68 because it's lacking capacity and the house drops to 67, and I need to double check on this, but I believe in both cases, that's when the heat pump shuts off and either the electric resistance or the natural gas kicks on. Does that answer your question?
Yes and no, right? Because I mean, otherwise, I mean, it's again more, and this is more specific to our service territory, right? But natural gas is the most cost-effective option from a customer standpoint, and then again, not necessarily just looking at the emissions piece, but customers may run the natural gas furnace longer, to a lower set point, rather than the heat pump.
Well,
Is that taken into account as far as, or could that be taken into account, I guess I should say, in the model?
well, essentially the model is making the decision to use the heat pump if it can, to preferentially run the heat pump. If you use the gas furnace more, right, then depending on where you are, you'll get a different result. I mean, we could change the controls in the model. That's possible. But I mean, so if you're talking about, like, if we go to like slides, if we go to the results for the, I skipped it. Wait, you're talking about like Minnesota, Wisconsin, right?
Washington.
Oh, Washington, Pacific Northwest. Okay. Yeah, you can see, you mentioned essentially at the moment, because there is coal operating on the margins in Washington, regardless of which heat pump option you choose, there's still an overall increase in emissions in 2019, right? So if you were to run the gas more, right, then this might improve. But essentially, this is a study looking at, can we use heat pumps and reduce emissions? So we didn't look at options where you would use the natural gas more than you needed to.
Yeah, and I guess that's just what my question kind of focused on the turnover when you would actually go from, the gas furnace to the heat pump being, the heat pump to the auxiliary on the gas, right? But if the model's already taken that into account to utilize the best option to meet the 67 degrees or above, then that's fine.
It preferentially, different controls could be programmed. The way the model is operating is to use the heat pump to meet the load when it can. Yeah.
Okay. Thank you.
Mm-hmm.
Great. And I think the last question I see here, unless other people want to raise their hand, is from Kevin, and I'll just ask it. He was curious about what your next study is.
So we have some current funding from NRDC to continue with this type of analysis, except that we are going to be looking at different grid scenarios. So for example, if we don't have coal on the grid and we have a certain amount of renewables, what does the situation look like? So we'll be doing that for a residential analysis, and then we're also going to be doing like a medium office building scenario. And we hope to have that in December, January, something like that.
Great. I think I see one more. Jerry, did you raise your hand here? I'll unmute you. Jerry Ryan. You there, Jerry?
I'm sorry. I know you addressed.
That's okay.
I just wanted to be clear. In all scenarios, was the 80% furnace the gas backup, or was in the variable speed a higher efficiency used?
No, same furnace in all cases.
Okay, thank you.
Great. All right, I'm going to take a quick look. Any other raised hands?
See if they'll let me off the hook.
Excellent. All right. Well, we have one more. Will the upcoming office study consider gas heat pumps, the one you just mentioned?
No, that's not in our work plan.
And then Brad asked one too, will you further expand this to look at the additional impact of HPWH? Not sure, is that?
Oh, heat pump hot water heaters. Actually, yes, that is included. That is included in our work plan for the NRDC study I mentioned.
Great. Okay, well, with that, we're letting you all go 10 minutes early. Thanks so much for watching and being a part of the discussion on this. And thanks, Theresa, for presenting. We will get you guys all a link to the recorded version once that's posted. And feel free, Theresa's email was in the chat if you wanted to follow up with any specific questions. All right,
Okay.
thank
All right.
you.
Thank you.
Take care, bye everyone.